of you may be aware that I'm kind of a nerd. And it might not surprise you to learn that I might or might not have been recently flying one of those new fancy multi-copter drones with a GPS-based return-to-home failsafe. Now, if you lose radio signal, that thing just flies back to the location where it originally took off. Pretty cool, huh? Well, the problem is I was flying from a boat. So, by the time return to home might or might not have happened, the original reference location was just a bunch of water. So, if you're doing signal integrity analysis and you're using ground as your reference point, you should think about what I just said. Ground may not be as great a reference as you think. Hi, I'm Amelia Dalton, host of Chalk Talk. Today, ground bounce and a lot of other power-related issues can have a big impact on the validity of our signal integrity analysis. What we need is a power-aware SI so we can keep track of that slippery ground when it tries to drift away. My guest today is Brad Griffin from Cadence Design Systems, and we're going to chat about power-aware SI analysis. Before we get started, don't forget to click that link. There you can find out all about power-aware SI analysis from Cadence Design Systems. Hi, Brad. Thank you so much for joining me today.
It's my pleasure, Amelia. Thanks for having me.
Okay, Brad. Now, I've been hearing a buzz lately about power aware. Now, can you fill me in? What do you mean by power aware?
Excellent question, and I agree with you. It's a hot topic these days. But I do have to say this, not everybody has a good understanding of exactly what that means. And so before we kind of get into what's happening in the signal integrity world, let's talk about what that actually is. Then we'll go into why people are doing it, and then, of course, then how you can do it.
Excellent. So can we first start talking about what's made this an important issue today?
Yeah, very good question, because signal integrity has been something that's a process that's been in place, 20 plus years now. And the thing about it is we've made some assumptions to be able to get the job done faster. And one of those assumptions has been ideal power and ground. Just look at the signal, the signal only. Don't worry about if the power or the ground is changing the voltage at all, because ideally they're going to stay the exact same voltage all the time. Now, of course, we introduced power integrity somewhere along the line and looked at low impedance power delivery networks, but those were always separate tasks.
Yeah.
But what's happened today is that with DDR, especially in memory interfaces, the things are just getting faster and faster. On top of that, because the requirement in our cell phones is to use less power, the voltages are getting smaller. So when signals get faster and the voltage swing is actually less, some of those assumptions we had about ideal power and ground, those are bad assumptions now. They can actually impact the overall signal quality. What you'll find is that when a signal goes from a 0 to a 1 or a 1 to a 0, it changes its state, is there's going to be some kind of power droop or ground bounce that affects that. And when you have multiple signals doing, there's simultaneous switching noise, and it makes a big issue in today's modern memory interfaces.
All right, Brad, power droop, ground bounce, you lost me. What's going on there?
Yeah, so like I said, these are kind of new topics. They've been around forever, but we tried to just sort of sweep them under the rug for many years.
Okay.
And what the deal, like kind of in the simplest possible way of looking at this, is that when you measure a signal and it's the voltage that it's at, it's going to be done in reference to ground. So
right.
that, the signal, whatever the ground is, the signal is going to be that much above the ground. But when that ground is rippling, that actually affects the signal, and the signal ripples as well.
Right.
And so when the current is changing, like it does in these very high-speed interfaces very quickly, that current change actually causes a ground bounce or a power droop. If that happens at precisely the wrong time, like when the signal is switching from a 0 to a 1, that can actually cause the data that's being written or the data being read to be read incorrectly. So instead of getting a 0, you get a 1. And depending on what kind of a system you have, that could be a big problem, like a banking system or something like that. You don't want that to happen, right?
Yeah.
Given this has been an issue, these effects have always been there. But if you go back like 10 years when DDR2 was first introduced, DDR2 400 had a 1.8 volt swing. Now, that's still pretty small, but given the fact that at 400 megabits per second, or that's 200 megahertz, the risk of error was still relatively low. You had margin to play with, I guess is the best way to look at it. But fast forward to today, or actually last year when DDR4 3200 was announced, I mean, that's screaming, right? And then they lowered the voltage to 1.2 volts. That's 1/3 less. 1.2, 1.8 doesn't sound like that much, but if you realize that's 33% less, and you're 8 times the data speed, that risk of an error due to ground bounce or power droop is significantly increased. And so therefore, you really need to simulate that to be able to see what those effects are so you don't suffer the problems in the lab.
Sure. Weren't you saying something earlier about simultaneous switching? Is that different than ground bounce?
Great question, and it's not really different. It's just the impact of multiple signals experiencing the ground bounce. So I kind of like this analogy of, imagine a firefighter with a hose out there, and he's trying to solve the problem, put out the fire, and he's got the fire hydrant pumping the water, and everything's going great. Well, now what happens if there's 64 guys trying to squirt from the same fire hydrant, right?
Right.
Basically, you don't have as much energy. We always like to compare electrons to water in the signal integrity world. So really what you would take a look at is any signals transitioning from 0 to 1 or 1 to 0, you have a ground bounce problem. But inside the chip, what's happening is there's a capacitor that's charging or discharging that I/O. And that's what's causing it to happen. And the faster this happens, the more opportunity you have that capacitor is not either going to fully charge or fully discharge.
Right.
And if one capacitor doesn't make it, then okay, there's a small amount of ground bounce or power droop. But if 64 capacitors don't make it, then there's a greater amount of it. So that's the simultaneous switching problem that we deal with. And so again, let's go to the DDR4 bus. Think of 64 bits transitioning simultaneously at 3200 megabits per second. And then only this 1.2 voltage swing. You can see why a signal integrity engineer can't just look at the signal alone. He's got to look at signal and power together. And that's why power-aware signal integrity is becoming such a hot topic.
So I think I have a reasonable grasp on the electrical principles, but what makes the analysis tools power-aware?
Okay, very good question. It's something that we've been dealing with for a few years now. And kind of go back to this idea of signal integrity tools, just looking at the signal, but assuming that the power and ground was ideal. Well, okay, the job of the signal integrity engineer today doesn't change that much in the fact that he's still looking at the signals, but the tools can no longer assume ideal power and ground.
Right.
That's really the big change here, is that the power and ground assumptions are thrown out the window. So the tools have become much more sophisticated. They have to model that return path. So when the signal gets from point A to point B, the electrons have to return back to the source through the return path. And so we have to model that, because that's effectively that current returning. That's how the I/O capacitors get charged. If we don't model that whole thing, we're not really going to be able to model a power-aware signal integrity environment. That's one part. And the second part is the signal and the power and the ground, they all interact. You can't model one and then the other and pretend that they don't interact. You have to model them all together.
Right.
And so you need tools to be able to do the extraction that looks at the signal, power, and ground together as a single model. So the power-aware signal integrity solution actually has two major improvements. One is that the modeling of the I/O, where those capacitors are charging up each signal or discharging very quickly, they have to use a new form of modeling called power-aware IBIS models.
Okay.
We actually ratified this almost 2 years ago, I think, in the IBIS 5.0 specification. But the thing is, it's been slow for many I/O models to come to market that support this specification. But the more and more are coming online today, you need to make sure that when you're performing your simulation, that your vendor, whether it's a memory vendor or whether it's your memory controller vendor, they're providing a power-aware IBIS model. And then, of course, the tool has to understand all the stuff that's happening inside that model.
Right.
The second piece is the actual interconnect itself. Every little A to B connectivity has to be modeled very accurately.
Yeah.
And so whether you're extracting from the chip, and when I'm talking about the chip, I'm talking about from the I/O to the actual output of the chip or the bump, and then the package, basically the bump to the ball, and then the PCB pin to pin. You have to have each one of those three pieces. You have to model that very accurately. And again, not just the signal, but signal, power, and ground all coupled together.
Right.
That's kind of the big piece of what the tools need today to be able to perform this function.
Okay, so Brad, can you give me some examples of the top reasons signal integrity folks need to move from ideal power ground simulations to power aware simulations?
I would love to. In fact, would it be okay if I gave you a top 10 reasons?
Yeah, that's great.
I think that there's a number of different reasons. I can't guarantee you these are the top, but let me look at the issues here. Is the simultaneous switching noise that we talked about, that impacts bit error rate. And
right.
bit error rate's an issue that we'll talk about in a little bit, but it's certainly the signal integrity engineers today care about this. Memory interfaces is all about the timing. You got to have your strobe and your data. They have to all be lined up properly. If there's any power ripple, that's impacting it. So therefore, you don't get accurate simulations unless you're doing power aware. Ripple on power and ground, that affects the signals. If you're not modeling them together, power aware and extraction, then you're not getting accurate results.
Sure.
Eye masks, which is something that's become JEDEC requirement in DDR4 and LPDDR4. If you don't have the ground balance model properly, you're not going to get an accurate result in the eye mask. Therefore, your JEDEC measurement requirements are going to be inaccurate. Another reason is talked a lot about the data bus because we want to make sure the data is accurate.
Sure.
But there's also an address bus. You have to say, what address do I want to pull this data from? Well, address buses are now transitioning from one address to another very quickly as well. So we don't just have 64 data bits we have to worry about. We also have 64 address bits.
Right.
Problems getting bigger. And so you have to be power aware to understand that whole thing. Number 5, I mentioned this already, sort of this old technique of doing ideal power and ground and then saying, well, there's enough margin built into this that I can get by.
Yeah.
Guess what? Doesn't work anymore. And because of that, numbers 4, 3, and 2, you're going to spend more time debugging your boards if you haven't actually solved this problem in the design and analysis phase.
Sure.
So more times in the labs, you're doing more respins, which eat up your engineering budget. And then number 2, you're going to impact your time to market because everybody has to get a design out on time.
Right. Number 1 here, don't leave me hanging,
Oh,
Brad.
number 1? Oh, yeah, well, of course. Number 1, you don't want to lose your job because risk is you never want to be that guy.
No.
We didn't get our product to market because we couldn't accurately read or write memory. You
Right.
don't want to be that guy. So you have to look at all this if you want to be on top of your game and meet the latest and greatest JEDEC specifications for DDR4, LPDDR4. You don't want to lose your job, so be power aware.
So, Brad, I take it you might be able to recommend a set of tools to help them keep their jobs?
Oh, Amelia, I thought you'd never ask. Yeah, of course. So I'm happy being at Cadence for the last 12 years. I've really seen the signal integrity solution really advance. And for a couple of years now, we've been talking about power-aware signal integrity. The technology's all in place. We've been advancing it the last couple of years to support the latest DDR4, LPDDR4 specifications. But we really have a system in place that really supports the whole ecosystem. So depending on whether you're a chip designer, a package designer, a PCB designer, or a system analysis, we've got the right tool in place to be able to sort of address that. So real quickly, you need to create those power-aware IBIS models. There's a tool called T2B. You need to be able to extract from the chip. There's a tool called Excite PI. You need to be able to extract from the package. There's a tool called Extract IM. And then you need to be able to extract from the board. There's a tool called Power SI. So each one of those has a certain input that would be different. So if you're a chip designer, you're going to have certain data available to you. If you're a package designer, you're going to have certain data available to you. So the package, they have this information. The output is a power-aware model that can be used by the system designer so he can plug it all together and actually perform the analysis that says, hey, this whole system from literally I/O to I/O, it meets the JEDEC requirements for DDR4 and LPDDR4.
All right, Brad, but does it really work?
Oh, Amelia, would you really doubt me?
Well,
No, I guess we wouldn't be the first EDA company to make grandiose claims stuff, but I'm happy to say that, working internally at Cadence, we've actually validated all this technology. That's kind of a cool thing about Cadence, the depth and breadth of the company. We have an IP team who's actually a leading provider of DDR IP. And so for them to be able to provide IP to their customers, they've had to build a test package and a test board. They had to test it in the lab. You go to any of these conferences, like upcoming MemCon conference, you're going to see a test environment where they've got package and board, and you're going to be able to show you the latest LPDDR4 functioning at specification.
cool.
All that was validated using Sigrity technology.
Nice.
So we trust the solution because we use the solution. So we know that we can actually provide this to our customers with the knowledge that it works.
So the IP group simulates using Sigrity, but how do things look once they build a test board and take it to the lab?
Yeah, excellent question. I mean, that's probably any signal integrity engineer wants to know. great results, but does it actually correlate? Good news is, we've worked with some partners in the industry, Tektronix for an example, to be able to capture these results. So we actually have a LPDDR4 or DDR4 test package. It sits on a board, and the same simulation results that we showed previously, we've actually captured all that in the lab to see how close we actually are.
Oh, okay. And how does the simulation and measurement line up?
Actually really good. That's the great news here, is that we can take it in the lab and we can see results that are basically within 5%. And that could be just little measurement results, or maybe some sort of difference in the way that we actually measured it versus captured it in the simulation. But still, if you can get that good in the design phase, it gives you that confidence that you can actually take your product to market and build it and not have to spend those long days and nights in the lab and meet your time to market requirements.
Impressive. So it seems like Cadence not only sells tools, but they depend on them for their own products. Is there anything else about your solution that my audience should know about?
I think that, with DDR4 and LPDDR4, it doesn't just sort of stop at power aware. This whole Moore's law, getting twice as fast, and we're really kind of butting up against the edge of it with parallel buses and DDR4 and LPDDR4. LPDDR4 actually has a 300 millivolt swing. It's becoming very challenging. And so there's new things that JEDEC specification has put in place. And one of them is bit error rate. I think we mentioned that earlier in our top 10. So we've never had to do this in memory interfaces before. We've done it with serial link, like PCI Express or serial ATA, but you've never had to simulate really the hundreds of thousands or millions of bits that it takes to do a bit error rate test with memory interfaces. The good news is, since we've done it with serial, Cadence has actually been able to take that technology and sort of tweak it and make it work for single-ended memory interfaces as well. So we can do a bit error rate test for DDR4 and LPDDR4. So that's a big advantage that our customers are taking advantage of, and that they're able to meet that requirement, not have to get in the lab and find out if or not they meet the bit error requirements.
Right.
Another one that we actually learned about working with our IP team is you get to these really high-end 3200 megabits per second for DDR4, or actually LPDDR4 is headed to 4266 megabits per second. The data is transitioning so fast. When you're transmitting over copper, there's going to be loss.
Sure.
And so when that signal actually gets to its destination, you can't really even see it, what it was. So you need some kind of equalization to boost the signal to actually capture it, whether it's a 0 or 1. So modeling equalization is, again, something we've been doing in the serial world for a while. And the way we typically do that is with an algorithm called IBIS AMI, Algorithmic Modeling Interface to the IBIS. So we've actually taken AMI and hooked that onto memory interfaces as well. And so now we can actually model the boost at the TX or the CTLE at the receiver to make sure that we're able to capture exactly what's happening inside the chip. Because these are things that you don't see on the board, they actually happen in the chip. So you need some kind of algorithm to model that. So we put that in place to support LPDDR4 and DDR4 memory interfaces.
All right, Brad, put a bow on this bad boy for me.
Well, again, I thank you very much for the chance to talk with you, Amelia. It's been a really great run at Cadence the last 2 or 3 years since we acquired Sigrity, and being able to do power-aware signal integrity analysis. Many customers are depending on this. Our DDR team depends on this. And so really any modern system needs to look at power-aware. If you're relying on sort of the older methodologies that rely on ideal power and ground assumptions, you're really putting your job at risk, number one, but you're also putting your company's profits at release. So I really want to encourage your listeners to make sure that their tools they're using support power-aware IBIS models and have power-aware interconnect models. And of course, if they don't have that today, they can always come to Cadence. Our Sigrity technology is more than capable of supporting them. It works in-house. It works for many customers. So at that moment of truth, when you go to the lab and you want to make sure that your DDR4 bus is working properly, you're going to always wonder, was my signal integrity solution power aware? Well, if you're using Cadence technology, you can be Sigrity sure that it was power aware.
Awesome. Well, I think that's all I have time for today. Thank you so much for joining me, Brad. It's always awesome to talk to you.
Likewise, Amelia, thank you.
Before we go, don't forget to click that link. There you can find out even more information about power-aware SI analysis from Cadence Design Systems. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, check out EE Journal's YouTube channel, keyword EE Journal, or the on-demand section of eejournal.com.